This is Parental Podcast number 62, and this is the second part of the review of active flow control devices for vehicles. And we're picking up from podcast number 61, the part one of this series, from this figure here. So the Bugatti Veyron and how its rear spoiler and the ride height change with speed. And if you haven't listened to that podcast, you can just go back and listen to that. And we're looking at this paper here, a review of active aerodynamic systems for road vehicles. So let's continue on. And we're going to do, in the first part, we looked at a bit of the history, and now we're getting into almost modern times now. So looking at this vehicle called a HSR2, it's a production vehicle based on the Mitsubishi 3000 GT, it seems. And it's really cool because it has a bunch of different aerodynamic features. For example, it has at the front, the splitter plate can move up and down or like out a bit more. The back of the vehicle, like around the base of it, where you have like near the wheels, you have another sort of splitter plate looking thing, but that's just to make it flush with the ground almost. Then at the front, you have canards. These are little wings that come out near the headlights, and then they have end plates to reduce the induced drag or the vortex drag that comes off of those canards, which are producing lift or downforce. Then at the back, behind the like the cockpit bit, you have this effectively just a flat plate that can just be popped up at an angle to increase the downforce. So there are a bunch of different active flow controlled features here. In fact, the splitter plate you can move depending on what you want. So that's quite amazing. So they say here, the characteristic feature of the HSR2 was the use of a number of movable aerodynamic elements to change its aerodynamic characteristics to match the current road conditions. So the following were mounted on the vehicle: a chin spoiler, two retractable canard wings, so they're retractable, that's pretty amazing, two independently controlled flaps, and a rear underflap. The flaps could be swung by an angle of 20 degrees or 30 degrees. So that rear underflap, that's near the diffuser. The paper presented the results of the tests performed in three different driving conditions. In the high-speed curve driving condition, all individual movable aerodynamic components were active. So in other words, they were all deployed. In contrast, the canard wings and flaps present in the pair were activated only on the car side of the inside of the curve. The flap was turned by 20 degrees. So depending on how you're turning, you can deploy certain features and not others. So the experiment showed that an increase in the drag coefficient of 0.095, an increase in the downforce of 0.11, and an increase in the side force coefficient of 0.02 in this configuration compared to the configuration without any of these elements. So the drag coefficient increase of 0.095, because this is for a high-speed curve, that's not that great because you don't really want to increase the drag too much because you don't really want to brake too much. But considering that you're getting a downforce coefficient of 0.11 increase, that's an acceptable increase potentially. And then the side force is quite good as well. To have an increase in the side force means that it helps you kind of stick to the ground a little bit in a sense. So it means you can corner a bit faster. So during acceleration, the chin spoiler was extended and the drag coefficient increased by 0.01, while the downforce coefficient increased by 0.02. So that's not too much, but it's better than a poke in the eye. When you want to accelerate, you don't want to have drag increasing. You want to have a bit of downforce to make sure that the tires don't slip, but it really depends on the vehicle. So during braking, all elements were active, which caused the drag coefficient to increase by 0.21 and the downforce coefficient by 0.42. Both flaps rotated at an angle of 30 degrees. So during braking, you want to have an increase in drag coefficient, and that's quite good to have 0.21 increase. That's like pretty much doubling. Well, it's probably like for this car, it's increasing by about 50%, 60% perhaps, the drag coefficient overall. So that's a massive increase. Now we get to different flow control devices. We're going to be looking into the different features. So for example, we're looking at the change in aerodynamic lift force by forced flow separation. This is a very interesting idea because usually we try to increase lift by keeping the flow attached. So by inducing flow separation, you can actually increase the lift momentarily or the downforce, and that's what one of these angles was about. So they say increasing the rate of change of aerodynamic forces can be achieved by a route other than rotating airfoils. A couple of researchers presented the results of a numerical study on the phenomenon of flow separation around a wing designed to rapidly generate changes in aerodynamic forces. The purpose of this research was to establish how much change in the lift and drag forces can be obtained using force flow separation. So in other words, this is effectively dynamic stall. And there's a whole body of research on this, and ways that wings dynamically stall do vary. But in this particular instance, they have a multi-element setup. They don't just have one wing, they have two wings. And they consisted of something called a GOE 525 airfoil as the main element, and then another one of these behind this other airfoil to make a two-element airfoil. So the GOE 525 airfoil is quite an interesting airfoil. It's not that common from my experience. I had to look it up to see what the lift curve slopes were. And it's quite interesting because at low Reynolds numbers, it doesn't actually perform like a regular airfoil. It's very varied, the performance. For example, at a Reynolds number of 50,000, the lift coefficient is like almost zero at 0 degrees angle of attack. And then like when it gets to about 5 degrees, it just jumps up by like 0.5. So it's very discontinuous, and then it sort of goes on its way, and then it sort of jumps around a little bit. But then when you increase the Reynolds number to about 150,000, then it starts to stabilize. So its performance becomes much more similar to a typical airfoil lift curve slope that we're familiar with. So it's just a fairly linear one, and then a regular stall drop off. So it's interesting that this airfoil doesn't really perform very well until you get to a certain Reynolds number range. And the maximum lift coefficient of this airfoil was about 2.1. So it is very high. So they say the accompanying increase in drag is the cost with this phenomenon of dynamically stalling these wings. But when they were able to dynamically stall the wings, the maximum lift value, the lift coefficient was 3.8 at an angle of attack of 21 degrees. That's huge. So as I mentioned, the original lift coefficient maximum was about 2.1 or so, and comparing this to like a NACA 0021 or NACA 0012, they're in the range of about 1.4 to 2. So to be able to generate 3.8 is huge. And the way that they induce this flow separation is that they have these holes going through the wings at certain points. So the first element, they have 3 holes near the trailing edge. Then the second element, they have 1 hole or 2 holes near the leading edge. And so this allows the flow to separate in a way that produces so much lift, or so much downforce in this particular case, because they're upside down. So in addition to analyzing the changes in aerodynamic forces, these pressure distributions on the surfaces of the airfoil and the flow structures around the airfoil were analyzed. 2 different flow detachment structures were recognized. Air injected through the slots, so these holes at the trailing edge and the leading edge, but air injected through the slots placed on the main element of the airfoil caused the separation only on the main element, leaving the flow on the secondary element unchanged. So that's interesting to note. The injection of air through the slots placed on the second element caused strong flow separation on both elements. So that's quite interesting that the downstream element has more of an effect on the upstream element than the upstream element has on the downstream element, which is often the exact opposite of what it should be. But in this case, that's quite funky flow physics. They say that the injection of air the changes in the lift coefficient of 1.0 were obtained, which correspond to a 10-degree change in the lift coefficient of a NACA 0012 airfoil. So that's the equivalent change. So it's massive. The large changes in lift force that can be induced very quickly without rotating wings suggest the possibility of using this method in car body vibration damping systems. In racing car designs, the use of forced liftoff leads to a decrease in the lift force of short-span high-lift wings, and despite the accompanying increase in aerodynamic drag, a reduction in the resultant drag is achieved. So why is that? The reason is because they say the reduction in the induced drag overcomes the increase in the general drag being produced due to pressure drag increases. So for an airfoil, for those of you who don't know, there are 3 main types of drag for a subsonic airfoil. Let's say a very subsonic airfoil below compressibility, so it's incompressible flow. There's skin friction drag, there's pressure drag, and there's induced drag. The skin friction drag is from the flow going over the surface, and we're quite familiar with that. The pressure drag is due to a pressure differential on the surface upstream compared to downstream. And so if you have a high pressure upstream compared to downstream, there's a net force pushing the object back. Then there's induced drag, and induced drag occurs due to, in this particular case, because it is an airfoil, it's due to the production of lift. And then that creates vortices on the wingtips. That's what we're familiar with. So all these three components are really competing with each other. And on typical airfoil, the induced drag on the regular conditions contributes about 40% of the drag coefficient of the entire drag coefficient. The pressure drag contributes maybe about 20 to 30%, and then the friction drag corresponds to the rest of it. So in this particular case, by reducing the induced drag a lot, you can overcome the increases in the pressure drag that you're incurring, resulting in reduction in drag. So let's move on to movable flaps. So the position of the flaps on the vehicle, they looked at a typical, kind of like a Le Mans kind of type vehicle, which is just a fairly flat shape with a central cockpit. And then on the trailing edge, they put these flaps at different positions. They varied them in terms of how close they were to the to the back of the car, how close they were to the sides of the car, and how close together they were. So there are two flaps at the back. They can either be next to each other, or very far apart, or at the back of the car, or at the just behind the cockpit. And they also investigated how moving these flaps, whether you move them around the leading edge or the trailing edge, you rotate them, how that affects the flow. And it's really amazing, because what they found was that if you have the flaps, first of all, if you have the flaps close to the edge of the car, to the back of the car, that increases their downforce, their effectiveness when you move them. If you have them closer to the cockpit, that reduces their effectiveness. They also found that if you put them close together, let's see here, they say that placed close together, they are much more effective than if you put them further apart. And if you put them to the sides of the vehicle, they are not as effective as, hold on, let's see what they said here. And then putting them to the sides of the vehicle, that reduces their effectiveness as well. So you want to put them closer to, inboard. Now, in addition to that, the axis which they rotate about had a massive effect. So, as I mentioned, they tested them either on rotating about the leading edge of these flaps or the trailing edge of these flaps, how they rotate. If they rotate about the leading edge, two things occur. First, their performance is fairly predictable. It's fairly linear, and you can kind of understand, if you rotate these flaps by a certain amount, you can kind of extrapolate how they're going to perform. If you put them rotating about the trailing edge, that predictability drops off. It becomes a lot more unpredictable, their performance. However, the exact same trends still occur regardless of whether you have them rotating about the leading edge or trailing edge. So putting them near the back of the car, they still perform better compared to upstream. And that doesn't matter. That's not affected by whether you rotate them about the leading edge or trailing edge. So that's quite interesting. The second thing that occurs when you rotate these flaps around the leading edge compared to the trailing edge is that they become less effective overall. So interestingly, you want to rotate them about the trailing edge, which I didn't really expect, because when you rotate things about the trailing edge, you effectively have just this flap opening up, and you have this massive gap which all this air can just rush into, and it's going to create a lot of pressure drag. But this helps increase the negative lift. So that was surprising to me. And they went through and they talked about why this occurs. So if you have the flaps, let's say, for example, the flaps are upstream, so they're not right at the back of the vehicle. The reason why these aren't as effective as putting them at the back of the vehicle is because now at upstream of the flaps, you have high pressure, but downstream of the flaps, you have low pressure. So on the vehicle itself, you have both high pressure and low pressure zones occurring when these flaps are upstream of the back of the vehicle. So that means that you're not only producing downforce on the vehicle at certain points, you're producing lift. So they sort of cancel out a little bit. Whereas if you put these flaps at the back of the vehicle, that negative pressure is not actually on the vehicle anymore. That's behind the vehicle. So the vehicle is not affected, the surface of it is not affected by this negative pressure, whereas this positive pressure is still on the vehicle. So you get a whole downforce effect. There's nothing canceling it out. Now, when you put them far apart, these flaps, some of the low pressure region now bleeds over the sides. And whereas if you put them closer together, more of this high pressure is caught on the top of the vehicle. So that's why you're getting more downforce. So that was quite interesting. That was a nice way of summing it up. They say that the best placements for the flaps is at the rear edge of the vehicle, and the solution was used in the Porsche 908 and 917 cars. And they also mentioned that the Pagani Huayra, I can never pronounce that properly, has movable flaps at the rear and front of the body. So now let's move on to movable supporting flaps. So a few researchers, they proposed the specific use of a small movable element in the form of a flap placed on the body under the airfoil which interacts with it. So in English, if you have a rear spoiler, and imagine you've all seen these young kids who they first get their cars and they put this massive, like when they're like 18 or something, and they put this massive rear spoiler on it. So imagine that, and on the regular car, and then underneath it on the boot or the trunk, the lip of it, you have this little flap, maybe 5 centimeters or 2 inches thick, just popping up and just like a little strip going across most of the back. That's what this flap is, and it can go up and down. And what they found was, as I mentioned, that this actually significantly increases the downforce of the entire setup. The aerodynamic characteristics of a car with an inverted wing generating aerodynamic downforce as a function of its angle of attack were studied. After adding a small movable aerodynamic element, that little element at the rear edge of the trunk lid under the wing, it was found that the aerodynamic effects of that itself rotated at 55 degrees, corresponded to the effects of the entire wing rotated at 15 degrees. So that tiny little thing, which is like, I don't know, takes up maybe 10% of the surface area of the entire wing, is almost as good as, let's say, a wing which is only 4 times the size. So it's very effective. So let's move on to movable gurney flaps. So a gurney flap is if you have an irregular airfoil, at the trailing edge, you just have this like little flap that like goes 90 degrees. It's this little dodgy thing, but it is very beneficial for aerodynamic performance in certain cases. They say it was shown that a gurney flap placed on the wing operating close to the ground has a much higher lift than the one placed on the wing operated far from the ground. So in other words, the ground effect is a massive proponent of the gurney flap operation. The lift generated by the gurney flap depends only on the lift coefficient and not on the aerodynamic profile of the wing. That's really amazing. So, in other words, you can have whatever wing you want. It doesn't really matter. As long as this wing is producing a lift coefficient of whatever, like let's say 0.5, the gurney flap is going to be affecting it in the exact same way, they're saying. That's quite amazing. Moreover, this coefficient depends on the angle of attack of the wing or the wing ride height. A reduction of the wing distance to the ground dramatically increases the influence of the gurney flap. This was only possible for the front wing. So we have a picture here, as I mentioned, just these wings, these inverted wings, and then at the trailing edge you have this little like vertical flap popping up. It's very tiny. So for F1 cars, the flow structure from the front wing affected by the gurney flap will interact with the other car components with evident aerodynamic performance changes with respect to the baseline configuration. The overall front wing downforce increased by almost 24%, while the drag force increases by 28%. So is that a good thing? It depends. If you're going around a corner, then that's very good. First of all, you have an increase in downforce, which means you can corner harder, and you have an increase in drag force, which means you can brake quicker. One of the things that really determines how quick you can go around a lap, but around a track, is how quickly you can brake. If you can brake quicker, it means that you can travel into the corner faster, and you can throw off that speed quicker, and then you can get around the corner without spinning out. So that, in particular cases, is very beneficial, this 24% increase in downforce and 20% in drag force. Let's move on to movable vortex generators. So a researcher called Joseph Katz, and I don't know if I've met this researcher actually. I've met someone called Joseph Katz. The problem with Joseph Katz is that there are so many of them in the world. Like literally, if you go into Google Scholar and you type in Joseph Katz, it will come up with like 10 different entries, 10 different people in engineering and all within like the aerospace sector as well. And they're all done very well in terms of their research. So it's hard to tell how many Joseph Katz there are in the world and who they are. Maybe deep down, we're all Joseph Katz. I don't know. But anyway, this Joseph Katz presented the operation of vortex generators. I actually did 2 podcasts on this, podcast number 60 and 59. You can check those out. But these vortex generators, which in some cases can be used as fast and efficient generators of various dynamic forces, particularly in the area of the chassis in the front part of the vehicle. So opening or closing the vortex generator plates can produce large changes in lift. So depending on the height of these vortex generators, they can either, they can dramatically increase the downforce. So that's one active flow control device. Now, we get onto one really cool one. It's called movable side force aerodynamic actuators. So what these things are, if you just imagine like a regular vehicle, and then on the A pillar, so the pillar that holds the windshield, you just have these flaps that pop out. And then around the sides of the front of the car, near the wheels, you have more flaps that just pop out as well. And these are these movable side flaps. And they look very unaerodynamic, but they do serve a purpose. They say the spoiler located on the A pillar at higher deflection angles generates a significant aerodynamic downforce, a coefficient of about minus 0.2, and a small lateral force, minus 0.1. So that's pretty decent. A small yaw and pitching moment are generated. Its effect is not only due to the forces generated on it, but also due to the creation of an area of increased pressure on the windscreen and an area of reduced pressure on the side window. The tilting side flap located in the front of the front wheel operates in a similar manner. So let's talk about why these flaps increase the pressure on the windscreen. So if you think about the windscreen just without these flaps, when the air is hitting it straight on, so let's say you put this car in a wind tunnel and then you have the air hitting it, there's going to be a certain region on this windscreen where the flow decelerates to zero, so stagnation. However, as you move closer to the edges of the windscreen, the flow is still going to decelerate, but not as much. And the closer you get to the edges, the less it's going to decelerate. Why is that? Well, let's just think about the flow to begin with. If you have all this flow, imagine you're the flow and you're traveling along and then you hit this wall and you have to travel around it now because you want to get around still. You have all this momentum. So you're going to take the path of least resistance. And if you're near the edges, that means you can still like roll around the A pillar and still keep a lot of your flow speed. If you're at the center of the windshield, you can't really go anywhere because you have flow to the left of you, to the right of you, up and down. And so you're just really stuck there. And that's why you're going to hit the windscreen and you're going to throw off all your speed and you're going to stagnate. So depending where you hit the windscreen, you may be able to get around it without losing much speed, or you may not. Now, that means that some of the windscreen has a stagnation region, other parts of it do not. When you put this flap on the edge of the A pillars now, you effectively increase the width of the windscreen. And so that means that less air, or more air in fact, can't move around the A pillar because it's now stuck because you have air right next to it and it's like, move out of the way, I can't get around. But the other air next to you is like, well, I'm trying to get around too. And so everyone's trying to get around, but there's only so much room and so much time to get around, and so you're just kind of stuck there. So that's why more of the windscreen will have a stagnation pressure or even a higher pressure because more flow is decelerating. That's an anthropomorphic analogy there for you, why this occurs. So those are movable A pillars. That was pretty cool, or panels on the A pillars. Now we move on to the final part, which are flexible elements generating aerodynamic downforce. So flexible components which can deform as a result of pressure differentials due to the body flow, or which can utilize compressed gas sources located on the body or the board of the body, can be active actuators of aerodynamic systems. Flexible elements can be efficient and fast reacting aerodynamic actuators in the proper configuration. So here they have a car, and underneath the front of the car, they have like an airbag kind of thing that increases and reduces the distance of the vehicle effectively to the road. What this does is that it means that you get less flow going underneath the vehicle, and it effectively helps produce something called a Venturi effect. Now, coupling this with two other elements on each side of the vehicle, between the two wheels on each side, you now have these airbags forming, which then kind of block off the car to the road, so it kind of makes it flush. that also helps increase the Venturi effect. So what happens now is you have a limited amount of area. The air going underneath the car is kind of now stuck underneath the car. It can't bleed out from the sides because of all these different panels here blocking them out. So it can only go downstream of like underneath the car. And as they do that, they accelerate in flow, in speed. And that means the pressure drops, which then increases the downforce. So that's how these work. And there have been other flow control devices very similar to this throughout history. For example, I think it was around 1980s in F1, they had these side skirts as well, uh, which produced the same sort of effect. The problem is that they're a little bit dangerous because if you hit a curb, that then allows the car to jump up a little bit in height, which allows flow to escape up from underneath it, and then you lose your downforce, and then you're out of control. So they're quite dangerous in that sense, which is why they're not allowed anymore. I think, at least in part, there might be other reasons, but that was one of the major reasons, from what I know. So that's the end of this podcast. Make sure to like, subscribe, and check out the Atmosphere Hawk. If you do experiments, you want to make it as accurate as you can, and the Atmosphere Hawk makes it 4% more accurate for you. It's very easy to use. Link in the description. Peace out, amigos.